everybody doing? I hope you all slept well last night. I am actually still kind of tired because way too early in the morning I knocked water over and I had to scramble myself awake to clean it up before I ruined any of my wood furniture or technology. So, make sure to keep beverages outside of the reach of your sleep-deprived small arms. Morning, word otherwise. Before we get started today, does anybody have any questions? Okay.
Wait, what time or when is the lab due? Tomorrow, right?
Yes.
At what time?
Midnight, they have it somehow in some format in tomorrow. Good question, though. Thank you for reminding me. So, I've been getting a lot of questions about lab, and as I've been saying, we do have lab this week, but our first lab assignment is one that is just a short algebra exercise, which has been brought to my attention could be done remotely anyway, and that's why I posted it to the internet, to be able to be done remotely if you so choose. There is still lab this week. You just don't necessarily have to come to this room on your laptop to do it. As long as you can access it on Brightspace and do it remotely, you may. But keep in mind, this is still a lab assignment. It will be due by the end of the week, and this counts as your lab, and under normal circumstances, if you're able to come in person, there will be a physical experiment in here. It's just, this was our first lab anyway, and it just happens to be one that could be done remotely. There is normal labs. This one's kind of an exception in that way. So make sure, especially next week, to start reporting to this room at 1:30 on your assigned lab day if you're able to be here in person. If you are not able to be here in person, please tell me as an individual and I can work out an alternative assignment for you. As for this week's lab, since it's just the algebra exercise, as long as I have it in some form, either you can come here during lab this week to work it with me physically, and I'll be here to answer your questions, in which case you can turn in a paper copy then. If you do it remotely, you can submit it to me via email, as long as I have it by tomorrow. And that'll count as your first lab grade. Next week, I am planning a physical experiment within the bounds of our rules and regulations at the moment. I'm trying to figure out how to modify our old marble cannon experiment so that you guys can still shoot something out of a cannon. So, stay tuned for that. And I lost my train of thought. Did I ask the original question? I didn't realize I did. I started again. Okay, thank you. Any other questions? Okay. All right, hope you're all having a good day. And I believe we regularly off. Thank you. Scalers and vectors. This is what the difference in class lengths is sort of I want to make sure that's slightly longer so we cover slightly more to make us confused as to where. So, when last we met, we addressed the concept of vectors versus scalars. Everything you measure, every number, is either a vector or a scalar. It is a scalar if it doesn't have a direction, if it's just a magnitude. And go ahead and put that up on the board. Magnitude, when I refer to that in this class, refers to a number. the magnitude of something you measure represents, it is the number. If I measure, that meter stick over there is 2 meters long, the magnitude of that measurement is 2. So everything you measure has to have a magnitude because that tells you how big it is. The whole point of measuring it is to determine how big it is. Scalars have magnitude, and that's it. All scalars is, any scalar is just a magnitude. It just tells you how big the measurement is. If you measure the mass of something, you've just determined how much mass it has. But a vector has magnitude and direction. So all vectors have both a number and they tell you in what direction that number is pointing. So you can usually draw a vector as an arrow. So let's say this arrow here represents a velocity of 10 meters per second north. The 10 is going to represent the magnitude, and the north represents the direction. So this is a vector. All vectors need to have both. Granted, all measurements have to have a magnitude because if you didn't measure anything, if there's no number, then you don't have a quantity. So if it's just magnitude, it counts as a scalar. And all of the variables we've been working with so far are types of vectors. Displacement specifically refers to I have moved this far in a specific direction. I have displaced myself in this axis in this direction. Velocity is specifically speed with a direction. So when you get in your car and you're driving, your speedometer tells you how fast you're moving, but the speedometer doesn't care what direction you're moving in, it just tells you the speed. So in general, speed refers to just the magnitude of how fast you're moving. Meanwhile, velocity is magnitude and direction. So your speedometer will only tell you the scalar speed. But if your car has the little compass in the corner of the rear view that says like north, northeast, that will tell you your vector direction. So is that a chair moving or is that like a speaker system? Okay, so 10 meters per second is a speed, is a scalar. 10 meters per second north is a velocity, is a vector. Acceleration is always inherently a vector because even if we're just looking at one-dimensional motion, if you are speeding up, you're accelerating forwards. If you're slowing down, you're accelerating backwards. So all accelerations have to be vectors by default. Every variable I give you, like the ones listed up here, I will tell you whether or not they are vectors. And in our formulas, if something is a vector, there's a couple different ways you can write it within a formula. Occasionally, you might see an arrow like this written above something, and that will tell you this is a vector because this little arrow here sort of represents that it has a direction. So this is one symbol that you might see periodically that represents vector. So if a variable has this above it, it is a vector. A similar symbol that is sometimes used, instead of putting an arrow on top, you just put a line under it. Either of those things, if you see them in my notes, in a note, in these notes or in a textbook somewhere, they all represent vector. Okay? All right. to give a specific example of that, these are some of the formulas we have been using so far in this class. The first two are the ones we've been using the most of. We're going to talk about the next two in a minute. Notice in these formulas, velocity, acceleration, displacement, velocity, they all have that little line under them. They are vectors. Although they are missing from this last formula, but in every other formula here they have those lines because they are vectors. These formulas are the ones we have been using. And these two formulas are very important. You're going to use them a lot. They're sort of foundational to the backbone of a lot of the other motion formulas we're going to be using. There's two more formulas that are also very important when talking about motion. And this physics department, for as long as I have been involved at PC, so going back at least to 2010, this department has liked to, because all four of these formulas are very important to understanding motion, the department likes to lump them together into one group of four, labeled as such because of how important they are. It's just been sort of a tradition in this department for a very long time, although when I was the first student coming here, the poster they used was the mid-2000s Fantastic Four movie poster. I have since updated it with a more recent comics cover, as opposed to the more recent Fantastic Four movie, which we don't speak of. Now, we've been using the first two formulas. We're going to go over the next two today. So, the first formula assumes something called constant velocity. If an object is moving at constant velocity, is it accelerating?
No.
No. Acceleration is defined as the change in velocity. This formula right here, if velocity is changing, this formula kind of breaks. Because if this changes with time, then the rate at which you are displacing is changing with time. And then this formula no longer works. So put a little asterisk in your notes. This equation only works for constant velocity. This formula works for changing velocities, because this is the acceleration formula. If you're accelerating, your velocity is changing over time. But this formula doesn't tell you how far you move while you're accelerating. When you get in your car and you turn it on and you increase your velocity from 0 to 60, do you stay still until you're at 60? No. The entire time your velocity is increasing, you are already moving. You displace some physical distance as your speed rises. You don't stay still until you're done and then you start moving. The entire time you're moving at some speed, it's just that speed is changing. So the entire time you are moving, but this formula doesn't tell you how far you're moving. This formula can tell you how far you've gone, but only under constant velocity. So neither of these formulas can tell you how far you've moved while you're accelerating. And that is what these two formulas are for. These two formulas sort of combine the previous two to be able to give you some sort of an indicator of how far an object displaces as it accelerates. Another example, besides just your car, displacing as it changes velocity. One of the things that accelerates you every single day, and will for the rest of your life, is gravity. We discussed last time that gravity acts as an acceleration. It causes acceleration in objects that are falling. When I drop this marker, it doesn't begin falling at constant speed. It begins accelerating towards the ground. The speed is going to keep increasing the longer it falls. And it is displacing the entire time it is falling. It's moving a distance even though its speed is increasing. And this formula will become incredibly useful for tracking a falling object because you can track how far it has moved as it displaces. which is one of the things we're going to start doing right now. I'm also going to write that first formula there up on the board because we are about to use it and I am about to tag away from this slide. I might need to clarify something. So the formula is, if I'm going to say it out loud now, delta x, the change in an object's location, is equal to velocity initial times time. So there's lots of different ways to write initial velocity as a variable. Because I had 3 different physics professors at this school, there's at least 3 different ways I've been taught to write it. And occasionally that comes through in my notes as well. VI, I will write to mean V initial. So this means initial velocity. But what's on the board there, V0. So this is supposed to be a 0, not a letter O, it's a 0. So sometimes I might add my little slash through it to make it clear that it's a 0. This is meant to represent the velocity at time of 0, at the beginning of the experiment. And because one of my professors is from South Africa, I occasionally refer to it as V naught. But that's not, I don't mean V N-O-T, I mean V N-A-U-G-H-T, which is to say velocity at the beginning before you start moving, it's your initial point. All 3 of these, this is what I might say out loud. I might say V naught or V initial out loud. I might write VI or V0. All of those terms mean the same thing, and they're so interconnected in my brain that they're all just interchangeable, which is why occasionally a different one's going to come out based on my mood. They all mean the same thing, and if it's ever unclear which one I'm using, or the fact that they're all the same, please ask the question immediately, stop me, and I'll try to clarify. It's just a quirk in my brain because of how I was taught. I see all of these, they mean the same thing, and so we just use them interchangeably. So, in that formula there, on this whole screen, any V sub 0 means the initial V at the beginning of the experiment. So, the displacement of an object over time is equal to its initial velocity times time plus 1/2 times acceleration times time squared. This formula can tell you how far an object is going to go, factoring in its speed at the beginning of the experiment, but also its rate of acceleration for the entire experiment. This formula is very, very useful for a lot of reasons, one of which being you can sort of simplify it for specific edge cases. Let's say the object we're looking at is moving at constant velocity. Would that object be accelerating? No. And then if we were to try to use this formula to tell us how far that object moved during this experiment, if it wasn't accelerating, this whole term could just go away because there's an A in it. If that A is 0, then it's just going to fall out. This whole thing would be gone, which just leaves us with delta x equals VI times t. With this last piece gone, does this first part look kind of familiar?
Yeah.
Yeah, what formula is this once you take the second half off? It's just the first formula again. You can rearrange V equals delta x over delta t to become just this first part. So this formula is just, this formula number 3 is just the first formula but expanded upon so that you can find the displacement while you're accelerating. But if your acceleration is 0, this falls away and you're left with what you already had. It's just a better version of the formula. Subsequently, you can also start from a velocity of 0 in which case this term would fall away, and you're just left with the beginning and this part of the end here. So there will be times where certain pieces will fall out of this formula, and it'll get smaller and easier to work. But with this part off, you've worked with this piece before. We're just adding on to it. To actually utilize it now, we've been coming to this slide and working these examples slowly over a period of days. We previously began looking at this question. We answered the first part of it. We're now going to answer the second part. So, we drop a stationary object. I'm going to redraw my fully drawn purple baseball. My purple marker is running out of ink. All my markers are running out of ink. If the ball begins as a stationary object, what is its initial velocity going to be?
0.
Very good. We did that last time. We know time in the air is 3 seconds. We found out previously how fast the ball was moving after 3 seconds. Now we're going to figure out how far it fell after 3 seconds. So, because it was accelerating, we couldn't use Formula 1. We now have Formula 3 that we can use to track how far it went. So we're going to start plugging things into this formula. We want to know its displacement, that's delta x. Its initial velocity is 0, so that's going to be 0 times 3, so this whole term is just going to go away, plus 1/2 times the acceleration. Because the object is falling, it's going to accelerate down because of gravity, and the rate of acceleration due to gravity is negative 9.8 meters per second squared. That's a constant you should definitely have written down. And the ball was falling for 3 seconds. Now keep in mind the time term in this part of the formula is squared, and you need to make sure when you're working it that you're only squaring the time. It is possible, if you put it into your calculator wrong, that your calculator might try to square everything here. But the only thing that needs to be squared is the time. I'm actually going to change this slightly. If you want to make sure your calculator doesn't make that mistake, I would write in parentheses and 3 squared end parentheses. Doing that, if you put this whole thing into your calculator and you write it like this, that will keep it from squaring everything. Just make sure to follow order of operations. You can do this one step at a time if you wanted to. I'll actually write down the next step myself if you need it for your notes. So this term is a 0 times a 3. It's just going to go away. This term here, we have 1/2 of negative 9.8. I'm going to simplify that to negative 4.9. 3 squared simplifies to 9. So this is just the next line. If you just want to put this into your calculator, you can. Simplify it down to avoid some issues with calculators there. And then this will tell us our total displacement as this ball fell. Which I don't have written down in my notes, unfortunately. And so, that is going to give us a final answer of negative 44.1 meters. If an object is left alone to fall in free fall for 3 whole seconds, this is how far it will have fallen. That's actually a lot. 1 meter is about 3.3 feet. So I did a quick conversion. This would be about 150 feet falling in 3 seconds, which is a lot. That's more than the length of a football field. If it feels like too much, keep in mind 3 seconds is actually a pretty long amount of time. When I do this, that marker's not even in the air for a whole second. 3 whole seconds of falling is an eternity. And that's why it fell this distance in that length of time. So, any questions about this formula, how we found that answer? Okay. I'm going to tab back to the formula page just for a second. The last formula there, formula number 4, is sort of the odd formula out. 90% of the time, you're going to want to use one of the first 3 formulas. This one is especially useful for objects that are moving and accelerating. This last formula is useful. I admit it's not going to come up super often, but when it does, you need it. This formula here is useful because it doesn't have time in it. So if you don't know the time something happened in, this formula suddenly becomes useful because you don't need time anymore. If time is not provided to you, this formula is what you need to use. Last time we did calculate the final velocity of the ball as it fell. Does anyone remember from your notes what that final velocity was?
I guess 28.4.
Thank you. 28.4?
29.
29.4 meters per second. We're going to rework the answer we just found using Formula 4 just to prove to you that it's going to work. So, Formula 4 tells us an object's final velocity squared will be equal to its initial velocity squared plus 2 times its acceleration times its displacement. Displacement, the d div, the delta x mean the same thing. Again, I'm sorry for the inconsistency in my notes. So, we know the final velocity because we solved for it last time. So we're just going to plug that in. Negative 29.4 squared. Again, make sure you're squaring this whole term. What happens when you square a negative number?
It becomes positive.
Very good. It's going to become positive. The negative is not going to be an issue anymore. What was the ball's initial velocity?
0.
0. So that's just going to be 0 squared. This term is just going to go away. That's going to leave us with 2 times our acceleration, which is negative 9.8. And then we're going to solve for displacement again, just to prove that this formula works. So, I'm going to simplify this down to the next line. Negative 29.4, if you square that, you're going to get positive 864.36. Our 0 squared term is just going to go away, so we're just going to leave it out of the next line. 2 times negative 9.8 is negative 19.6, and that's going to be times our displacement. So, the last thing we need to do just to get d by itself, we're going to divide both sides by negative 19.6. So d will be equal to 864.36 divided by negative 19.6.
Negative.
And that's going to give us, please double check this on your calculator, so you No orders. Negative 44.1. So both formulas work. They're just useful in different situations. D is the best formula that you have if an object is accelerating, you need its displacement, but you don't know how long it accelerated for. You don't know the time. Quick question, why is the negative on the answer important? Represents down, tells you direction. Very good. Since these are vectors, the negative is just really going to tell you forwards, backwards, up or down until we start doing more than one axis at a time. Yes?
That's negative in front of the 9.8, correct?
Yes,
Okay, just.
because that is also pointing down. Anything, when you define your system, when you start your equation and you say up is positive, down is negative, everything pointing down needs a negative sign. Now, we could work this and say down is positive and just take all the negative signs away, in which case we get a positive answer, but we previously indicated in such a case that down would be positive, and so it would still say down. It just depends on how you set up your system. I am going to try to consistently say down is negative just to enforce that into your head, and that will work. So, these first four formulas, these will be at the top of your formula sheets, which are located on the right space page. Any questions so far? Okay. I've been talking for a decent amount of time now, so I'm going to give you guys a quick break. We're going to get some water, go to the bathroom, and I'm going to run to my office to pick up the spare markers that I keep forgetting to bring in here. How's everybody doing? Any questions, issues, complaints, haikus? All right. So, real quick, let's address this last question, which we haven't talked about yet. It's been up there for a few days and I haven't mentioned it at all. So, when you ride a constantly spinning carousel, which is to say, You're basically on a platform constantly rotating around the center axis. So if you are spinning in a circle on some sort of device, in such a scenario, is your speed changing? If you're just sitting on your chair on the carousel going around in a circle? No, the machine goes at a specific speed. Once you get up to that speed, and you just keep sitting there, you're going to continue moving at it. But, is your velocity changing in such a situation?
Yes.
Yes, very good. Velocity is a vector, meaning it has to have a direction attached. All right, just make some more space. Here's my one eraser. I need to get more than one to leave in each corner of the room. So, this is the carousel. Let's say you're sitting here. If we freeze frame at this particular moment, normally you're just going around in circles, but we've frozen time right here. What direction is your velocity vector pointing in right now? Well, so all vectors point in straight lines. The carousel is spinning, so the carousel is rotating, and you are on the carousel. But at this exact moment, if you're looking forwards, if you were just thinking about just this one moment in time, what direction would your velocity arrow be? I did see someone make the correct gesture. It's just going to be a straight line. In this moment, your velocity would point forwards. But, you know, a couple of seconds later, when you've moved to here, what direction would your velocity be pointing in? Yeah, it's going to be a line that's always tangent to the edge of the carousel. Now, over time, this direction is going to keep changing and you're going to keep moving in a circle, but if we freeze frame it 1 second at a time, your velocity is always going to be a straight line tangent to the circle. Even if your speed isn't changing, your direction is. Therefore, your velocity is changing, therefore you're accelerating. You can accelerate even if your speed does not change. Your velocity will, but your speed might not. Changing direction still counts as accelerating. You have felt this before. Even if you've never been on one of these things, you've been in, I assume, a car. And how many of you have, say, made a turn without slowing down? Okay. I figure most everyone who's been behind the wheel of a car has probably done that at some point. Probably not recommended, but we've all done it. And your speedometer might not change, but you are still changing direction. And when you accelerate, you feel a force causing that acceleration. So when you make that turn, you kind of lurch in your seat because you feel the force causing you to accelerate. So, all direction changes cause a change in velocity, therefore all direction changes are caused by an acceleration. So, just addressing this last question. Make sense? Okay. Now, we've been talking a bit about gravity. It's come up in a couple of our examples so far. So let's go a little more in depth on that before we continue doing some examples about objects falling. Gravity is very important to life on Earth. It's good for you to understand it because it's going to be acting on you your entire life, which is good because if there was not a force keeping you to this planet, you'd fly off into the void of space, which is bad for humans. So, why do things fall? Gravity is the only major force acting on an object. The object begins accelerating downwards at the acceleration of gravity on planet Earth's surface. So, as we've been saying, the acceleration due to gravity on Earth's surface is -9.8 meters per second squared. And this is the rate at which all falling objects on Earth's surface are going to descend towards the ground and drop. This is a known constant, so this is the kind of number that I will make sure is written on your formula sheet, but it's a very good number to have in your brain because it's going to come up all the literal time. Negative means down because all objects on Earth's surface are going to fall down, and because it's related to gravity, and because it's its own unique constant, it does have its own variable, and that is g, lowercase g for gravity. So there are some formulas where it will specifically call for the acceleration due to gravity, in which case that formula will say g because it wants very specifically this number. This is a type of acceleration though, so there will be situations where you plug this in for a. So it's kind of a, if you see a g, it's always this number. If you see an a, it might be this number. This is an acceleration, it can be plugged in for a, but this is defined as g, it will always be plugged in for g. So do write this in bold in the corner of your notes. This is the rate at which things are going to fall. The rate at which the velocity will change as they are falling. This number does change somewhat when you leave Earth's surface. Ultimately, what causes gravity is it's a force between two objects with mass. So gravity is a force. There's a force acting on all of you. And that force is going to cause an acceleration. When you exert a force on an object, it makes that object accelerate. Like in baseball, when the ball is flying at you, when you exert a force on it with the bat, the ball accelerates. It was going this way, but then you hit it, and then it accelerates and turns around. So all accelerations are caused by forces. The acceleration of gravity is caused by the force of gravity acting on your bodies. So gravity is a force, but it causes an acceleration because of that force. And that force comes from the fact that Earth is a planet with mass, and you are all objects with mass. Gravity is a force between any two things with mass, meaning there's technically gravity between these two markers right now, but because these things have very small mass, that force is incredibly tiny. The nearest, most largest object to all of us is the Earth, which is why the thing we get pulled to is the Earth. So the Earth's mass is enormous, and that is why we get pulled towards its center. Additionally, because the Earth is round, and because most of its mass is located in its center, that's why gravity is always going to point towards the center of the planet, no matter where you are on its surface. And I have one more point. Where to go? Oh, that force also depends on how close two objects are. For example, the sun has more mass than the Earth. The sun is bigger than the Earth. But does the sun's gravity pull us off of Earth's surface and towards it? No, we're closer to Earth, so the more direct force on us is going to be from Earth. That does mean if you get on a rocket ship and you start flying away from planet Earth, this number is going to start dropping because the force of gravity will be weaker, therefore the acceleration of gravity on your body would be weaker. But as long as you are within Earth's atmosphere, as long as you are not literally heading towards the moon on a ship, we're going to assume that this number is going to be constant for anything happening on Earth. All right? So, again, write this in bold in your notes. Now, let's see. An object's weight is literally the force of gravity acting on it. So, all of the weight of any object is literally just the force of gravity pulling down on it. And acceleration is just due to that force acting on that object. Now, regardless of an object's weight, so I have a weight of about 1,000 newtons. This marker has a weight of barely any newtons. Sorry, the metric unit for force is newtons. The imperial unit for force is pounds. So let's say I have a weight of many, many pounds. Meanwhile, this marker has a weight of only like 1 pound, not even a whole pound, less than a pound. I weigh a lot more than this marker. But if I and this marker were both dropped from a building at the same time, we're both going to accelerate at this rate. This is the rate of free fall for every object on Earth, ignoring air resistance. If you drop a ping pong ball and a bowling ball off of the same building at the same time, are they going to hit the ground at the same time? They will, actually. Weight does not change this. An object's weight does not change this number. Mass affects weight. So the mass of an object will change how much it weighs, but the acceleration that that object will fall at is always the same. Barring extreme cases of air resistance, for example, single pieces of paper. So if I drop these two things at the same time, the paper is going to fall slower because of extreme amounts of air resistance. It's got a lot of surface area and not a lot of mass. The paper there is the abnormality. Ignoring air resistance, every single object is going to fall at that rate, regardless of its weight. If you drop me, a bowling ball, and a golf ball off of a building at the same time, we all hit the ground at the same time. Got it? Okay. And we're going to mostly ignore air resistance in this class because it's a pain to calculate. So across the board, everything, unless I tell you otherwise, is going to fall at this acceleration. Cool. All right. We're running along last time, I think. Yes. Okay. Yeah. Next slide is an example, which we will use to begin with next time. Any questions as you guys are packing? Yeah, my office, or class tomorrow. If you're still working on it Friday night, yeah, under my office door. Is it done now?
Yeah.
Yes. Wow.
Do you know if we have a meeting?
Yeah, in general, if you're doing a remote lab, I will accept it in any format as long as I have your answers and your work.
Oh, did he? I haven't seen
If
it.
you're doing it as a paper copy, just give me the paper. If you're doing it digitally, you can put your answers in the document and you can email it to me. And I also now have an example of someone who just wrote their answers on a separate sheet of paper. That is also fine, as long as I have them. Again, if you have lab this week, you can do it remotely. That said, I will be here if you want to do it in person because I will be here to answer your questions. Thank you as well. Everyone have a wonderful day. Hello? Yes. You emailed me earlier? Right. So this is the assignment. I'll extend it by a week for you because they've all had a week to review something. All right. So this I will take from you by next Friday. And I can also extend your first homework and quiz assignment as well. But you are going to need to access the online tool that we're going to be using for our digital homework, which is Sapling Learning. I believe I wrote this in the email, but I'm just going to.
I went ahead and signed up for that.
Oh, all right. Were you able to find the class?
Okay, I like solid homework and quiz. I just
Okay.
need to do the lesson for this.
Right. So I I'm recording these so that you can rewatch them if you need them. Additionally, if you're able to access the course Brightspace page, which is just our school's sort of online learning tool.
I don't know if they enrolled me in your like space class yet.
Oh, okay. Yeah, I've had issues with students coming in after the fact and then not being here. If you email me about that, like if you send me another email, I can then forward that to the Brightspace department and they can make sure you're in.
Okay.
But just to show you what you should be looking for once you get in, if you click on individual, this tab here shows you all the introductory material, this blurb about how the class will work, so this information sheet. Each individual chapter is going to be located beneath that. That's where I will post links to all my recorded lectures and these slides, so you can access them outside of class.
Cool. And what lecture should I go through to complete this?
This first one.
Okay. All right.
And again, I will extend that assignment and your homework and quiz next week.
All right. Thank you.
You're welcome.
Hello. You said quizzes, sorry. Quizzes in like 5 senior grade, right?
Yes.
Okay.
And there's
So it's
about
not like
10.
significant.
It's incredibly insignificant. It's just good practice.
Yeah, because I accidentally did a quiz instead of the homework. And I didn't know what I was doing. So I'm pretty sure no, I didn't do well. But it doesn't.
If you give me your full name, I might be able to play with, like, give you an extension on
If
it.
it's like significant, I think
Okay.
because I got like practice with the homework. I did all the homework. It was good.
Okay.
And then I the quiz was bad. I was just making sure.
Yeah, each quiz is like 0.5% of your total grade.
Yeah. Yeah, that makes sense. All right. Appreciate it. Thank you.
You're welcome. Have a good one.
You too.